So in this video, we're going to talk about how to present a system of linear equations using matrices and why this approach is useful when solving systems. Okay, so let's begin with a system of three equations in three variables like this. So now solving this system using substitution or elimination is possible, but as the number of equations grow, those methods become time consuming and also error prone. So that's where matrices comes in. So a matrix is a rectangular array of numbers and we can use it to write entire system in much more compact and organized form. So let's take this system and try to write this system as a matrix. Okay, so to do that, the first step you have to do is you have to write the coefficient matrix. Okay, what is coefficient matrix and how do we get the coefficient matrix? Well, to do that, you have to focus only on the coefficients of the variables x, y, and z on this system. So let's take the first equation. So let's try to extract the coefficients of the variable x, y, and z. So in the first equation, the coefficients are -1, +1, and 2. And for the second equation, the coefficients are 1, 2, 1. For third, it's -2, -1, and 1. So what you have to do is you have to extract these coefficients and then you have to put them in this format. So here the first, if you take the first column of this matrix, this numbers contains the coefficients of x variable. So this is the coefficient of the x variable in the first equation. This is the coefficient of the x variable in the second equation. -2 is the coefficient of x variable in the third equation. Similarly, if you move into this column gives you the coefficients of y variable in these three equations. So it's 1, 2, -1. Those are numbers here. And this is with z variable. So this is how you get your coefficient matrix, and we write that in this format. So now let's move into the second step. The second step means that you have to add the constants as a new column. So now what we do is we bring the right hand side of the equation, which is this side, and on this side we have three constants, 0, 6, and -6. What we do is we add them as the fourth column to the matrix, separated by a vertical bar to indicate that they are not part of the coefficient matrix, but rather they are augmented part. So this gives us the augmented matrix. So this is called augmented matrix. So this augmented matrix holds a lot of information from the original system, just in a more structured format that is perfect for raw operations. Okay, so next question. Why we use matrices when we are solving a system like this? First, it helps us to keep the system organized, especially when dealing with a lot of equations and a lot of variables. Second, it sets stage for a powerful solving techniques like Gaussian elimination or Gauss-Jordan elimination, where we systematically use raw operations to reduce the matrix and solve for the variables. And third, the matrix method are the foundation for many computational algorithms used in science, engineering, data analysis, and more. In fact, computer softwares like MATLAB, uh, Python, and graphing calculators rely heavily on matrix-based solutions to handle the large systems effectively. So in summary, if you have a system of equation like this, to make it into a augmented matrix, what you have to do is, first of all, you have to come up with your coefficient matrix, which means you have to extract coefficients from your equation, and then you have to put a separate column for the constants with an bar like this. So this is we call augmented matrix. So moving on, so now that we have seen how to represent a system of linear equations using augmented matrix, now let's talk about the next important step, that is transforming a matrix into a form that makes solving a system much easier. So this special format is called row echelon form. So why is this row echelon form important, and why do we use it? So let's take a look at this system. So this is the corresponding augmented matrix for this system. As you can see, the, the x coefficient for the first variable is 1, and we don't have any x variable here, so the coefficient is 0. Similarly, over here also x coefficient is 0. So likewise, I have built my coefficient matrix, and then I made it at the augmented matrix by putting my constants. Okay, so this is the augmented matrix. So notice something interesting here. So this matrix over here is nicely arranged. So the leading entries of each row moves to the right as you go down, and everything below that main diagonal of the coefficient part is 0, right? So also the diagonal entries, if you take the diagonal entries over here, they're all equals to 1. So this makes it easy to perform back substitution. So this is what we call a row echelon form. So formally, any augmented matrix that has all ones or zeros on the diagonal and zeros below the diagonal is considered to be a row echelon form. So row echelon form means in the diagonal you should have like ones or zeros, and all the elements entries below the diagonal should be have zeros. So a format like this we called as row echelon form. So this form is the goal when we use Gauss elimination method. So once we reach it, we can quickly solve for the variable using back substitution. So now we understand what row echelon form look like. So now let's learn how actually we get there. So once we have a system of equation and we know how to get into augmented matrix, and now we talk about row echelon form. So how do we get from augmented matrix into a row echelon form? That's what we are going to discuss now. Okay, so to transform a matrix into a row echelon form, we use something called matrix row operations. Matrix row operations. So these are simple rules that allow us to manipulate rows without changing the solution of the system. So there are three basic row operations, and they are corresponding. They are corresponds directly to the familiar equation operations. So the first operation over here is interchange of two rows. So the first operation is actually interchanging of two rows of a matrix. So this is just like swapping two equations in a system. So it doesn't change the solution, but it might help us to simplify the system to get a better pivot position. The second operation is multiply a row by any non-zero constant. So this is like multiplying both sides of the equation by a number to make the leading coefficient 1. A very common step when we are aiming for row echelon form. The third operation is probably the most important operation out of these three. So adding a multiple of row to another. So this is how we eliminate variables below the leading ones in each row, turning entries below the diagonal into zeros, just like elimination. So why these operations matter? So together with these three operations, it gives us a tool that we need to reshape a matrix step by step into row echelon form. So once we there, we can easily solve a system using back substitution. Okay, so now let's try an example. So let's try to use matrix row operations to solve this system of equation. So again, here again we have three equations with three variables. So we have to begin this problem by writing the augmented matrix for this system of equation. So first of all, let me write my coefficient matrix, which start with 2, -3, 1, 1, -1, 2, 3, 1, -1. So this is the coefficient matrix, but I have to make it into augmented by putting my constants. Okay, here we go. So this is my augmented matrix. Okay, the first step, as we know, first of all, we should have uh, a one for the first entry. So to get the first row that has 1 in the first column, so what we can do is we can interchange row 1 and row 2, because in row 2 we have 1 in the first entry. So what I'm going to do is I'm going to interchange first row and the second row. So I'm going to put that operation in this format. So row 1, so this notation I'm going to use for row 1, and this is for row 2, and with this notation I'm going to say I'm going to interchange row 1 and row 2. Okay, so I think it is easy for me to copy this down. First I'm going to copy this down and I'm going to paste it over here, and then I need to change the rows. So I'm going to take this and I'm going to move here, and I'm going to change first row into here, and this is going to move into the first row. And also I have to do the same thing with these constants as well. Okay, here we go. I just changed first and the second row. Okay, so now we need to get zeros as the first entry in the second row and the third row. We need zeros for these rows. So to get zeros as the first entry in the second row, what we have to do is we have to multiply the first row by -2 and add it to the second row. Okay, so we have to, in order to get rid of this 2, what I'm going to do is I'm going to multiply the first row by -2 and I'm going to add it into the second row. So this is how I'm going to put that operation. So I'm going to multiply this first row by -2 and I'm going to add into row number 2, and then that row will be our new row 2. Okay, so I'm going to take a new color and I'm going to write the numbers. So if you multiply first row by -2, I'll get a -2. Here, if you multiply -1 by -2, you'll get a +2. Here, +4. This is going to be a +6. So what I have to do is, in the resulting augmented matrix, you have to replace this whole second row by adding these two numbers. You have to add -2 to this 2, and 2 to -3, -4 to 1, 6 to -1. Okay, so let me copy this down first. Okay, and I'm going to paste that over here. Okay, this seems, I want to, I'm going to change the size. Okay, and I'm going to move this over here. So I'm going to erase row number 2. The updated row number 2 will be, you have to add these two together. It's a 0. So the first entry is going to be a 0. And you're going to add 2 with -3, which will give you a -1. And -4 plus 1, a -3. And 6 with -1, a +5. Okay, so this is your new augmented matrix, or this is the updated version. Again, you have to do a similar calculation to get a 0 over here. To do that, you are going to multiply the first row by -3 and you're going to add it into the third row. So this is how I'm going to write the operation. I'm going to multiply the second row by R1, and then I'm going to add it into R3, and R3 will be replaced by a new set of numbers. Okay, So let's multiply the numbers by negative 3. So this is going to be negative 3, positive 3, a negative 6, a 9, because if you multiply negative 3 by negative 3, it's a positive 9. So you have to add these these numbers together, and you have to replace those by new positions. Okay, again, I'm going to copy this down. It will save me some time. Okay, and let me erase this part because these are going to update. So over here you have to add these two numbers. It's a 0. Let me put a 0 over here, and you have to add 3 with positive 1, which is a 4, and then negative 6 with negative 1, which is negative 7, and then you'll have a 18. Okay, so now we have zeros over here. Now let's move into the second column. So this is fine, but we have to make this as a positive 1. So to get a 1 in the second entry in the second row, we multiply the second row by negative 1. So you have to multiply R2 by negative 1, and you have to replace it with negative R2. Okay, so I'm going to copy this down again. I'm going to paste it over here. But now I need to multiply each entry with negative 1. So if you multiply negative 1 with negative 1, you'll get a positive value. So these are positive, but the last one, it's going to be a negative. Okay, great. We are in this. We are making some progress, but still we need to get rid of this 4. So we have to get a 0 as the second entry in the third row. So to do that, what we are going to do is we are going to use the second row. We're going to multiply the second row by negative 4, and we're going to add it into the third row. So R2, you have to multiply it by negative 4, and you have to add it into the R3, and that will give you your new R3. So again, I'm copying this down, and let's paste this one. Okay, before we edit that, so let's multiply this by negative 4, and over here if you multiply by negative 4, it's a negative 12, and this is positive 20. So now you have to add these numbers. So here negative 4 plus 4, it's a 0. So this is 0, and then negative 12, negative 7, which is a negative 19, and then here it's going to be 38. Okay, now again we have to make this number a negative a positive 1. To do that, you have to multiply the third row by negative 1 over 19. So let's multiply R3 by negative 1 over 19. So if you do that, you'll get system something like this. So if I paste that over here, so if you divide this by negative 1 over 19, you'll get a 0 here. Sorry, a 1. And over here, it's going to be a negative 2. Okay, so this augmented matrix is equivalent to x minus y plus 2z equals negative 3, y plus 3z equals negative 5, and z is equals to negative 2. So the third equation gives you the value of z directly. So that means you can use the back substitution to get the values of x and y. So the matrix is now in the row echelon form. So this is in row echelon form, and this is equivalent to this system, and this system can be solved by back substitution. So if you do back substitution, you will get answers as x equals 2, y equals 1, and z is equals to -2. Okay, so now we discussed row echelon form. Let's take it one step further and introduce the idea of a reduced row echelon form. Okay, the reduced row echelon form of a matrix is even more refined version of row echelon form. So here's how you recognize it. So an augmented matrix representation with n equations and n variable is said to be reduced row echelon form if the diagonal of the coefficient matrix contains ones or zeros. So the diagonal of the coefficient matrix, it should contains only ones or zeros, and on the other hand all other entries in the coefficient part above and below the diagonal should be zeros. So that means each variable is perfectly isolated, its own way, and the system is essentially already solved. So while row echelon form prepares the matrix back substitution, reduced row echelon form gives you the solution directly. There's no extra steps involved. So this is especially useful when you're using Gauss-Jordan elimination, where the goal is to reduce the matrix all the way up to reduced row echelon form. Okay, so let's try some example with reduced row echelon form. So here this is in row echelon form because we have zeros over here and the diagonal of the coefficient matrix is 1. So this is row echelon form, but this is not in reduced row echelon form, because if it is in reduced row echelon form, these entries should be zeros as well. So what we are asked to do is you have to reduce this system into a reduced row echelon form. So let's try this. Okay, so first of all, we need to get rid of this -1. It's because reduced row echelon means all the entries except diagonal should be zeros. So let's try to get rid of these two this -1. To do that, what I do is I see I have a 1 here. So what if I add the first row and the second row? And I'm going to replace new result with the R1. Okay, let me write that. So I'm going to add R1 and R2, and it's going to be R1, the row 1. So the result is going to be 1, and you have to add these two rows together. These columns together. 0, 1 plus 0, it's 1. -1 plus 1, a 0. And then 2 plus 3, a 5. And you have to add these two numbers. It's going to be -8. And other two other two rows are going to stay as it is, like this. Okay. So now I need to I need to remove this 5 and 3. So to do that, I am going to use this number over here. So what I'm going to do is I'm going to multiply the third row by -3, and I'm going to add it into the second row. So I'm going to take my R3, I'm going to multiply it by -3, and I'm going to add it into R2, and the result will be in R2. So let's multiply R3 by -3. So 0, 0, here you'll get a -3, and here you'll get a +6. So now I'm going to copy this down, and I'm going to paste it over here, and I'm going to erase these entries because they're going to update. Now I need to add these two together. So that will give you a 0. And then if you add these two numbers together, you'll get a 1. If you add 3 and -3, it's a 0 again. And if you add 6, -5, it's a +1. Okay, great. So now we have all the entries 0 except this one and the diagonal. So let me get rid of this as well. To do that, I'm going to multiply the third row by -5, and I'm going to add it into R1. So you multiply R3 with -5 and you add it into R1, and it's going to replace R1. So you're going to copy this down and you're going to paste it over here, and let's erase R1 because it's going to update. So let's multiply this by -5, 0, 0, -5 and a 10. So let's add these together, a 1 and a 0, and this is also a 0 because 5, -5, a 0, and over here you'll get a 2. Okay, so this is the reduced row echelon form. It's because the diagonal of this coefficient matrix is 1 and all the other entries in the coefficient matrix is 0. So this is in row echelon form. So if I if I try to translate this into an equation format, it says x equals 2, and here you don't have any y or z because the coefficients are 0, and the second y is 1 and z is equals to -2. So this is how you uh, reduce a system into reduced row echelon form and get the solution immediately. Okay, so let's try another example. So in this example, you have to solve this system of equation by using reduced row echelon form. So that means you have to first of all write this as a augmented matrix. So I have written the augmented matrix of this system. So this is the coefficient matrix, and these are the constants of the right hand sides. Okay, first of all, let's get rid of these. So here I have a 1. The first entry of the first row is 1, which is good. I don't have to do any simplification. But using that information, let's try to get rid of these values, the 1 and 2. The first step I'm going to do is I'm going to multiply first row with -1, and I'm going to add it into R2, and R2 will be replaced, and at the same time I'm going to multiply R1 by -2. I'm going to add it into R3, and R3 will be replaced. So let's try to do the both simplifications together. So starting with 1, 1, -1, 0, the second and third rows will change. Let's start with the first one. So you have to multiply this by -1, and then you have to add it into the second row. So if you add -1 with +1, you'll get a 0, and then -1, -2, -3, 1, -1, a 0, which is good, and then here you have a 6. Moving on to the third row. To get the third row, you have to multiply the second row, first row by -2. So it's going to be -2, -2, a +2, a 0. So let's add the numbers. So -2, +2, a 0. Here's 0. -2, 2, a 0 again. And here you'll get a 3. And here you'll get a 3 again. Okay, great. So now we have this form. We have zeros below this diagonal, but let's make these diagonals a 1. So to make this -3 a 1, what you have to do is you have to multiply the second row by -1/3. Here you have to multiply R2 by -1/3, and R2 will be replaced. Then you're going to go into R3, you multiply 1/3, and you have R3. Okay, so let's get our updated matrix. So you have 1, 1, -1, 0 in the first row. It's not going to change, but each entry in the second row you have to multiply by -1/3. So zeros are going to stay as it is, but this one over here will be a +1. and this is going to be a -2. Great. Now this row over here you have to multiply by +1/3. 0 is going to stay as it is. 3 gonna change as 1. Okay. Well, this is good, but still we have non-zero entries in this augmented matrix. So I'm going to remove this non-zero matrix using two more row operations. So to get rid of this, what I'm going to do is I'm going to multiply this row by -1 and I'm going to add it into R1. So you multiply R2 by -1 and you add it to R1 and R1 will be replaced. And to get rid of this -1, I'm going to add R3 directly into R1 and R1 will be replaced. So two operations. So let's start with the first operation. This is going to be the second operation. So let me copy this down. And I'm going to paste it over here. And first of all, you have to multiply R2 by -1. So this is going to be -1, this is going to be +2. So you have to add these two numbers together. So let me erase this part. So let's update this. It's going to be 1, 0, -1, and a 2. So now let's do the next operation, which is this. You have to add the two rows together, which is going to be, if you add these two numbers, it's a 1 and 0, 0, a 0, and then -1, a +1, a 0, 0, 1, 0, 0, 0, 1, and this is going to be a 3. It's a -2, 1. So now this system is reduced row echelon form. You can directly take the answers from this system. So this system says x equals 3, y equals -2, z is equals to 1.